All right, so this is Trig Math 120. We're going to be doing section 1.1 in this video, and this week we'll just be doing one section. Normally it'll be 2 to 3 to 4 sections a week, probably typically about 3. All right, so we're going to get through some basic notation, and then we'll talk about some interesting stuff. So basic notation first. If we have a point A, we have a point B, we can talk about a ray from A to B. So the notation would be something like this. So this is a ray from A to B. If we do it backwards, from B to A, that would be BA like that. So the order matters. Okay, we don't really care about rays too much in this class, but we do care about angles, and angles are made up of, an angle is made up of 2 rays. So if I call this guy A, I call this guy B, I call this guy C, then we can talk about the angle BAC. That would be this guy right here. All right, so the middle letter is the vertex of our angle. Okay, so if we also look at the angles CAB, that would be CAB. All right, so typically when we use this kind of angle notation, the order doesn't matter. And of course, the middle guy is still always the vertex. All right, by the way, when we do talk about angles like this, BAC for example, notice that actually there's 2 angles which can be described in this way. One is the one that I've drawn, this one right here, the one we typically think of as the angle when we say the word the angle. The other one is the one that goes all the way around the opposite way, right? Or not the opposite way, but the other angle, right, on the other side. So the convention is when we say the angle formed by 2 rays, we generally mean the smaller angle. So unless otherwise noted, we're always going to mean the smaller angle. So when I say angle BAC, I mean this guy as opposed to that guy there. All right, because this guy here is the smaller angle. All right, in terms of notation, for the names of angles, we're almost always going to use Greek letters. So theta, for example, oftentimes we'll use alpha, we'll use beta, we'll use gamma, but the convention is to use Greek angles or Greek letters. All right, so sometimes our angles are directed in that, so far we've just kind of drawn angles like that, right? There's an angle. But sometimes we actually care about angles, or sometimes we work with angles in terms of motion. So for example, we're thinking of maybe something that's starting out pointing in this kind of easterly direction, and then it's rotating and it ends up pointing in that direction. All right, like the hands of a clock or something like that. Of course, that would be, I guess, in the other direction clockwise. All right, so when we talk about motion, the direction of how we're moving matters, right? So if we're starting here and we're moving down this way, it's very different from starting down here and moving up that way. All right, so in those cases, we'll draw angles with an arrow like this, and instead of just no arrow like that. And also in this situation, there's the concept of kind of the start and the end, right? So in this picture over here, the start would be here and the end would be there, right? So a more technical phrase would be initial side here, and then here would be what's called the terminal side, or at least that's what our book calls it. Okay, so the start and the end. All right, so we'll be seeing this a lot because despite what you might think about trig, where it's just about triangles and angles and stuff like that, a huge application is about motion. A huge class of applications for trig is about motion, and so we very, very much often care about how our angles are directed, right? So again, this angle that I've drawn here is going to be often considered to be very, in a way, different from that angle there. Okay, depending on the application. All right. We're often going to be working with circles in conjunction with angles, especially again in the applications with motion. So oftentimes we'll have a circle like this. We'll have its center right there, and we'll want to consider angles that are that have vertex at the center. Okay. So in this type of situation, we call that guy here a central angle, or that's what our book calls it. In that it's kind of vertex is at the center of a circle, and in that case, this arc of the circle here is called the intercepted arc. All right. So in a way, the arc formed by that angle's intersection with the circle. So we'll talk about this concept, especially in the next few sections. We're going to want to know information like the lengths of these intercepted arcs and stuff like that. Okay. So again, this is just a mishmash of notation, but we need to get some kind of the foundational notation straight. So it's always clear what we're talking about. Okay, finally, when we do have angles, so let's say I have an angle here and I have an angle there, I have an angle here and I have an angle there, right? I have an angle here and I have an angle there. It's hard to compare them when I draw them, maybe even something like that, right? It's really hard to compare them when I draw them in all different kind of orientations. Okay, so for example, this guy right here, what is this angle compared to that guy right there, right? Are they the same? Is one bigger than the other? Which one is bigger than the other if one is bigger? It's hard to tell because of the way I've drawn my pictures. So one thing we very much like to do is to put angles into a standard position so that it's easy to compare them. So this standard position is where I take an axis, xy, so the plane, right? So oftentimes we call this the plane. Oops, the plane. And what we do is we put the vertex of our angle at the origin, and we put the initial side along the positive x-axis. All right, so right there. And then we put the terminal side wherever it needs to go. All right, so in this particular example, that would be my terminal side. All right, so in this case, this angle right there should be the same as that angle right there. Okay, so putting angles in this standard position is nice because if I do the same with this second angle down here, I can actually compare them, right? If the second angle has, I guess I need different colors here. All right, let's not do different colors. So this guy here, let's say is again, terminal side, right? This guy here goes to, let's say there, right? Then I can see that my first angle up here, let me just give these guys names. Let me call this theta, let me call this alpha, right? So in this situation, this guy here is theta, and that guy there is alpha, right? So I can see that the angle alpha is bigger than the angle theta, right? Whereas if I had them kind of twisted and turned in different orientations, it's hard to tell, and it's hard to work with, all right? So this is called standard position. So we often put angles into standard position so that we can compare them. Super important actually, because when we actually start doing stuff other than drawing pictures, when we start computing things with angles, we're going to want them in standard position because as you can see, if I draw here an angle in standard position, right, I don't actually have to worry about where the rays are, right? So if this is the same angle, let me make it so that they're kind of the same. If this is the same angle, just drawn floating on the page, then I actually have to kind of draw this side, the initial side, right? And I have to draw a terminal side. But when I draw things in standard position, right? The x-axis is already there. I only have to draw the terminal side. And in particular, I don't even really have to draw the terminal side. The kind of endpoint of the terminal side determines my angle, all right? So this point right there completely determines my angle, the coordinates of that point. And so that will make it very, very easy for us to compute with angles, because if I know the coordinates here, then I can calculate exactly how big that angle is, right? So if this is 3 comma 4, then I'm going to be able to figure out exactly how big that guy is. And that 3 comma 4 in essence describes how big that angle is, all right? Okay, so we'll be doing that very, very soon. But the idea of standard position is super simple, but yet super powerful. Okay, remember that, just a small note, if I have something like this, where this is my initial side and this is my terminal side, I could have standard position be, right, this is my initial side and that's my terminal side. So it doesn't always have to be above, in a way, my x-axis. This is the angle actually in this particular situation. All right. So let me write alpha, alpha. Okay. So those are the basics, just so that we could even just start talking about these things. Let's actually get into some more serious stuff. So now that we have this idea of standard position, right, we can always put in any angle that we work with into standard position. Let's actually start measuring things. So the traditional way to measure angle is with degrees. It's a terrible, terrible way of measuring angles, and we'll talk about better methods in the very, very near future. But for today, degrees. And I'll talk about why it's terrible when we get more into this. But for now, let's just work with degrees. So the idea of degrees is when you put an angle into standard position, right, and you want to kind of express how big this angle is, right? That's what degrees are for. And the idea is if you go all the way around full circle, that would be 300 degrees. All right. And anything less than a full circle is just whatever proportion you are out of the 300, or whatever portion of the 60 degrees you are. All right. So if a full circle is 360 degrees, for example, then if I just do a quarter of it, right, so an angle that goes from here to there, then that would be a quarter of 360 degrees. And a quarter of 360 is 90, so this guy would be 90 degrees. All right. Half of that, let's say half of 90 degrees would be, half of 90 degrees would be something like that, right? And that would be 45 degrees. Okay, so degrees, it's the measure is kind of straightforward. At least it has that going for it. Full circle is 360, and then you just take chunks out of the pie, right? Some common angles that we'll be working with are exactly 90 degrees, right? So this guy here is 90 degrees. If I go halfway around a full circle, that would be 180 degrees, all right? 3/4 way, 270 degrees, right? So 180 is half of 360. So this 270 is 3/4 of 360. And then, of course, we'll often be working with halves of these. So half of 90 degrees, as we set up here, 45 degrees. Oops. And here's one thing, always put the little degree symbol when you're talking about degrees, because, again, in the near future, we're going to be working with a different measure, radians, which is much, much far superior to degrees. And we definitely do not want to get confused as to whether we're using degrees or radians. So just like, if you're working with measures of length, you want to say 15 miles so that it's not confused with perhaps 15 kilometers. Okay, so anytime you're working with degrees, you absolutely want to put that circle. Okay, so 45 degrees is a very common one. This guy here, there's a lot of ways to think about what this guy here is, where, again, we're going 90 degrees and then halfway between 90 and 180. You could think of this as 90 plus of 45 degrees, right? Or you could think of this as 45 degrees, and then you're taking from here to another 90 degrees. Okay, regardless, you're going to get 135 degrees. All right. So you can figure out this guy here, and you can figure out that guy there. So those are some kind of common and natural ones, natural angles that we might come up, that we might see in applications. Another two very common ones we'll be working with are 30 degrees, so somewhere around here, and 60 degrees. Those two especially because it's going to turn out that computations with 30 degrees and 60 degrees are relatively simple. And so just in terms of kind of trig classes, it's very easy to have exercises and examples involving 30 and 60 degrees. All right. Okay. So that's the basics of kind of working with degrees. Notice one thing is that we can have negative degrees, right? So everything I've drawn here implicitly, I've meant, terminal angle and initial angle like this, right? Going this way. But we can have negative degrees. So this guy right here would be negative 45 degrees, where we're kind of thinking of that direction. Okay. In terms of the picture, you might say, why do I care about this? This is actually the same as if I went all the way around this way, right? So this would be what, 270 and then plus another 45, right? So this would be 300. This would be the same as, let me write kind of equal in quotes here, 315 degrees, right? In that they have the same terminal ray, right? But again, in practice, we might not want to consider them to be the same, especially when we're talking about motion, right? There's a big difference between if we're talking about motion where we start out in let's say here, and we move to there, compared to if we start out in the same place, but we move in the opposite direction. Okay, one is we're moving counterclockwise, the other is we're moving clockwise. We happen to end up at the same position, but kind of our motion was very, very different. So if we start here and we move down to our terminal angle here, we would like to, it's more natural maybe to express it as minus 45 degrees, as opposed to expressing it as 315 degrees, which would be, more natural if we traveled clockwise. Okay. Counterclockwise, rather. Okay, so this idea of different angles having the same terminal kind of ray is kind of encoded in the word coterminal. All right, so these two angles, minus 45 degrees and 315 degrees, are what we call coterminal. Okay, they're different angles, at least again in terms of applications like motion. They're different angles, but they have the same terminal ray. Okay, so there's lots of examples of this. It doesn't have to be negative versus positive. If I have an angle here, 45 degrees, right, and I think of this as motion like this, well, that's very different from if I go all the way around and then I go another 45 degrees, right? So this would be 400. So this would be 360 plus 45 degrees. So 405 degrees, right? So 405 degrees and 45 degrees are coterminal, right? They have the same, when you just draw their terminal rays, it's the same ray. But again, we often think of them as different angles in context of especially motion applications, right? In terms of motion, the first one, we're actually going around something fully 300 all the way around and then traveling a little further. Whereas the second one, we're just traveling a tiny bit. All right. So again, when you think about that in terms of travel, it's very, very different, even though they're kind of possibly drawn in very similar ways. Okay. So some of the exercises for this week, they'll ask you whether two angles are coterminal, And essentially the idea is, do they differ by a factor of 360, right? So for example, 0 degrees, just for a simple example, and 720 degrees, those two guys are coterminal because they differ by a factor of 360, right? They differ by a factor of going all the way around the circle. Okay. All right. Another way to say this is you can kind of subtract the two angles and see if the difference is a factor of 360. If the answer is yes, then they're coterminal. All right. That's maybe a way to describe how to actually check. All right. A couple standard angles. We give them names. So we've already talked about the 90-degree angle. And the standard name is right angle. And the standard way to kind of draw a right angle, we don't use the usual angle symbol like that. If it's 90 degrees, it's so special that we use that guy there. All right, we use a little rectangle to indicate a right angle. These are super important because right triangles are actually super important, especially in terms of the Pythagorean theorem. Okay, another angle we have a name for is the angle that goes all the way to the opposite side. So that's what we call a straight angle. All right. So far so good, right? It seems pretty straightforward. Working with degrees. We can have, like we said, 45 degrees, 78 degrees, let's say, 27.45 degrees. All of these guys make sense, right? 27.45 degrees would be 27 degrees. And then let's say in terms of motion, you rotate 27 degrees, and then you rotate a fraction of a degree more, all right? Let's say 15.47 degrees, right? So we can have kind of decimal degrees, and it's perfectly legit, no problem with this. But as it turns out, historically, people haven't used, there's an alternate way to talk about decimal degrees, let's say it like that. So historically, this alternate method uses degrees. So this alternate measure of degrees uses degrees for just the whole number degree. And then it uses minutes and seconds for the decimal parts. All right. So degrees, minutes, seconds. So this is our first kind of more concrete material. Okay, so maybe one explanation for this is that maybe people weren't comfortable with fractions. Maybe it has something to do with the fact that people were comfortable with time, right? With fractional, so minutes and second in terms of time, everybody's comfortable with, right? A minute is 1/60th of an hour, right? It's a fraction of an hour. And 1 second is 1/60th of a minute, right? So we're very comfortable talking about fractional hours using minutes and seconds. So perhaps, in the past, people kind of ported this to the idea of working with angles, in that they might be uncomfortable working with fractional, decimal angles. So they use the fact that they were comfortable with fractional hours and use it to in the context of angles. All right. So let's talk about this. So fractional degrees. Okay. Again, it's perfectly legitimate to talk about fractional degrees, and it's what we'll be doing most of the time in this class. 99.9% of the time in this class. But it's good to talk about this other way of expressing angles, in that it is historical, and we do see it in real life even right now. If you look at Google Maps or you look at a GPS device, oftentimes they'll be expressing degrees, not in decimals like here, 27.45 or 15.47. They'll be using degrees, minutes, and seconds. All right. So it's still being used today. Okay. So how does this work? Well, let's start with a simple example. 15.5 degrees. All right. So all right, sorry about that. So fractional degrees, 15.5 degrees. So what is this? This is 15 and, let me just write it in words, a half degrees. All right. So what is half a degree? Well, if we want to talk about minutes and seconds, if we want to break down degrees into minutes and seconds, the way we do it is exactly in the same way with time. All right. So the kind of analogy is we have degrees. Let me do the time first. The way we measure time is we have hours, and then we have minutes, and let's work with seconds a little bit later. So minutes, right? Let me put in seconds now, I guess. Seconds, right? So now we just do exactly the same thing. So before 1 hour, right, or 1 minute. 1 hour can be broken into 60 minutes, for example, right? And 1 minute can be broken into 60 seconds. Let me get rid of seconds, right? So now degrees, 1 degree can be broken up into 60 minutes. Okay, so it's literally the same. We're literally doing the same thing, except from hours to degrees. All right, so if you want to convert 15.5 degrees into 15 degrees and so many minutes, you do it in the same way that you do it with time, right? So 3 hours, 3.5 hours, right? How many, what is that in terms of hours and minutes, right? So 3.5 hours, 3.5 hours is 3 hours and 30 minutes, right? We're all comfortable with that. And it's exactly the same with degrees, all right? So 15 degrees, 15.5 degrees is 15 degrees, right? And a half degree, that's 30 minutes, okay? And our notation for minutes is like that, all right? So 15.5 degrees is equal to 15 degrees and 30 minutes, okay? So in a way, if you're comfortable with converting, decimal time into minutes, then you're in a way comfortable converting degrees, decimal degrees into minutes as well. All right. So 15.25 degrees, right? What is that? That's 15 degrees, right? And 0.25 is a quarter, right? A quarter of one. So it's like, think of it again as quarter of an hour. What's a quarter of an hour? It's 15 minutes, right? So this is 15. Okay. All right. So this is kind of a, intuitive way to kind of do this calculation where you're kind of just thinking about the relationship between hours and minutes, right, in terms of time. But we need, of course, this is a math class. We want a more concrete way to do the conversion. So let's do something like this. So 15.40 degrees is equal to what in terms of degrees and minutes? So how would we figure something like this out, right? Usually we don't think of, in terms of time, we don't think of 0.4 of an hour, right? So we don't naturally have an easy conversion from that to from 0.4 of an hour to minutes, right? So we need a kind of an algorithm or at least some mathematical way to do the conversion, a concrete mathematical way. Well, the right way to think of this, first of all, is the 15 doesn't matter, right? Because the 15 degrees is a whole number. So 15 degrees, 15.40 here is going to convert to 15 also here, and then a certain number of minutes. Okay? So first thing is the 15 doesn't matter. It's the 0.40 degrees, right? That gives us kind of the challenge. Okay? Now, the right way to think about this is, what does 0.40 degrees mean? that literally means, right, when we say 0.4, right, or 0.40, what that literally means is 40 over 100, right? 0.40, by definition, really means 40 over 100, okay? So this is 40 over 100 degrees, all right? When we say 0.40 degrees, it literally means 40 over 100, okay? Now, what about minutes? We want to convert this to minutes. How do we measure things in minutes? Well, 60 minutes is 1 hour, or 60 minutes is 1 degree, right? So we're measuring things in terms of 60 being 1, right? So instead of kind of 100 being a full thing, right? When we talk about 0.40, 40 over 100, it's now everything is out of 60, right? So if you think about this, that means that we're talking about a ratio here. So 0.44 or 0.40 is 40 out of 100 degrees. This is the same as we want it now in terms of minutes, and minutes is out of 60. So this is something over 60. Okay, so this is going to be our answer. This is the minutes that we want. So let me write the minutes that we want. Okay. So from decimal, everything is in terms of hundreds or tens or thousands, right? 40 out of 100 here. But when we convert to minutes, everything is out of 60s, right? So x out of 60. Okay, so if you can solve this algebra problem here, that x gives you the minutes. All right, and now this algebra problem is hopefully fairly simple. X equals 60 times 40 out of 100. Okay. And what is that going to be? Let's just very quickly do this. 64 out of 10. 6 and 10 cancel. 6 times 4. This is equal to 24, right? And so that means 15.40 degrees is equal to 15 degrees and 24 minutes. All right. Okay, so this idea of thinking about ratios here is actually super important. We're going to be using it next week when we do talk about, like we mentioned earlier, arc lengths, and we'll be talking about areas. The kind of formulas that we're going to get out of it come from thinking about ratios. Okay, let's quickly check this. Does this, formula or this technique make sense compared to the calculations we already know, right? So for example, 0.5 degrees. Does this turn out, with this procedure, give us, does it turn out to give us 30 minutes, right? We know it should be 30 minutes. So let's just quickly verify in a way that our technique does make sense, right? So 0.5 degrees, what does 0.5 mean? Again, 0.5 means 50 out of 100, or we could just say 5 out of 10, right? Same thing, of course, right? Okay, we want to express things, again, the argument here is we want to express things in terms of 60s, right? Instead of anything out of 10s, we want it in terms of 60s. So 5 out of 10 is equal to what out of 60, right? So these two ratios should be the same, right? And so when we solve, that tells me x is equal to 60 times 5 out of 10, which tells me that's 6 times 5, 30, right? And that's exactly what we expected. So 0.5 degrees is 30 minutes. So again, this is just a nice verification of facts we, in a way, already know. Okay. All right. Let's get a little more complicated. 15.47 degrees, right? How do we express this in terms of degrees and minutes? All right. So again, the 15 doesn't bother us at all, right? We know it's going to end up being 15 degrees and something. All right. So it's really the 0.47 that's interesting. What is 0.47? 0.47 is 0.47 is 47 over 100, right? And our goal here is to think of that in terms of 60s, right, as opposed to hundreds. So this is going to be something over 60. Okay. All right, if we solve this, we're going to get x equals 60 times 47 over 100 like this. Let's see, so this is 6 over 10 times 47. Let's simplify a little bit more. 6 out of 10 is 3 out of 5, right, times 47. And then now we can actually do some multiplication. So this is 141 over 5. And here's a problem, right? So this is not a whole number. What is this? If we actually calculated this, this is going to be 28.2. All right. So what did we conclude? We concluded that 15.47 degrees is 15 degrees and 28.2 minutes. All right. Not so nice, right? Not a whole number. So what we can do is we can break this decimal, this 0.2, down into smaller units. Right? So just like we break down minutes into seconds in terms of time, we can break minutes into seconds in terms of angle measurements as well. All right. So what's going to happen is we're going to take this 28.2. That's going to be equal to 28 minutes and then a certain number of seconds. All right. What are those seconds? Well, we have 0.2 minutes. 0.2 minutes. That's equal to, well, when we say 0.2, that's equal to 2/10, right? So 2 out of 10 of a minute. Okay. Just like with time, right? There's 60 seconds in a minute. So if we want to express things in terms of seconds, we're talking about ratios out of 60. So this 2 out of 10 should correspond to something, let me call it y since I used x above, out of 60. All right. So again, this 2 out of 10 here is kind of expressing decimals, whereas this y out of 60 is expressing seconds. All right. Okay, so ultimately, if I solve this algebra problem, 2 out of 10 equals y out of 60, I'm going to get the number of seconds. And this is going to be y is equal to 60 times 2 out of 10, which is 6 times 2, which is 12. Okay. All right, so ultimately we know that 15.47 degrees is 15 degrees, 28 minutes, and then 12 seconds. All right, and the notation for seconds is like that. All right. All right, so in terms of the procedure, it's relatively straightforward, right? So in summary, if you do want to convert a decimal degree into degrees, minutes, and seconds, right? The degree part stays the same, of course. For the minutes part, you do the ratio, right? The decimal, 47 over 100 is equal to something over 60, right? That something is going to be your minutes. And if your minutes happens to have decimals itself, then you can try to convert those decimals to seconds, right? Again, using the idea of the ratios, what over 60, right? There's nothing further than that. So if you convert to seconds and you get a decimal, traditionally you just leave it as a decimal. All right. So you might have something like 13 degrees, 47 minutes, and 12.5 seconds. Okay. Just like we do with time, right? We don't have kind of a name for something smaller than 1 second, or we don't have a special name, out of 60. In terms of seconds, right? We just use decimal seconds in that situation. So for angles, it's the same way. Okay. All right. What about going the other direction? What if I gave you something like, so let me write other direction. Right? So in other words, what if I gave you 20 degrees, 15 minutes, and 18 seconds, right? So this is an angle. How big is this angle in terms of decimal, in decimal degrees? Right? So this one is more straightforward because you have all you literally have you don't have to do any algebra to solve anything. The answer is in a way just conversion, right? So the degree stays the same, 20, right? What does 15 minutes mean? 15 minutes means 15 out of 60, right? So we're converting everything to degrees, right? So 1 minute is 1/60th of a degree. So 15 minutes is 15/60th of a degree, right? So this is 15 over 60. Okay, so everything down here is a degree, right? So I can even write 20 degrees, 15 out of 60 degrees. All right. Okay, what about 18 seconds? So there's two ways we can kind of think this through. One way is 18 seconds is equal to 18 out of 60 minutes. All right. Okay, and then now we don't want minutes, we want degrees. So what is 18 out of 60 minutes in terms of degrees? That's equal to 18 out of 60 degrees. All right. Okay. And so this is going to be 18 out of 60 times 60 degrees. So it's 18 out of 60 squared. Let me write it like that first. 60 squared. All right. And so that's 18 out of, if you square to 60, 3600 degrees. Okay. So ultimately this is going to be plus 18 out of 3600 degrees. Oh, sorry. Degrees up there. Okay, so this is how you could always do the conversions. The minutes go to, that number out of 60, and the seconds goes to that number out of 3,600. You could just remember it this way, but I think it's a very, very good idea to understand the reasoning that got us to this 3,600. All right, because if you understand this reasoning, then for example, if you can't remember the formulas or anything like that, you can always reproduce it yourself at will. All right. So this part right here, right? You want to make sure you understand this reasoning right there. Okay. And again, it's all thinking in terms of how we're measuring things and ratios. All right. Okay. So hopefully we're able to convert easily between our two different ways of measuring angles, degrees, decimal degrees, and degrees, minutes, and seconds. So the last chunk of this section is actually doing arithmetic. And this is really interesting. And you'll kind of see why in the paper homework for this week. So we explore this idea of arithmetic in kind of non-decimal systems of counting in the paper homework. And there's a lot of applications, especially relating to computers. So even though in our class and in real life, you're probably not going to be kind of doing arithmetic with degrees, minutes, seconds very much, if at all, ever. The stuff we're going to be talking about here is actually useful in other contexts. Okay, so what do I mean by arithmetic? Well, addition, subtraction, multiplication, division. All right, so let's start with addition. And again, in terms of decimal degrees, all this arithmetic is just straightforward, right? What is 15.2 degrees plus 0.3 degrees? It's just 15.2 plus 0.3, right? So 15.5 degrees, no problem. So the one that is kind of more complex is if you work in minutes and seconds. So 15 degrees, 28 minutes, 45 seconds, plus 12 degrees, 52 minutes, 18 seconds. What is that? Okay. All right, why might we care? Well, perhaps in terms of motion, right? We're talking about moving this 15 degrees, 28 minutes, and 45 seconds. And then we move a further 12 degrees, 52 minutes, and 18 seconds. And the question is, how much of an angle have we moved from our initial position. All right. So again, a lot of our applications can be seen through motion. All right. Okay, so how do we actually do this? Well, the good news is we kind of already know because we already know arithmetic, except we have to do a little bit of modifications. So let's just actually do it the way we kind of traditionally learned arithmetic, which is kind of to put things in columns, right? So 15 degrees, 28 minutes, 45 seconds, 12 degrees, 52 minutes, 18 seconds, and we're just going to add them like this, all right? Okay, now let's just do this. So one thing to note, of course, is these columns we have 3 columns here, and the columns should be kind of thought of as separate from each other. So we add them column by column. And let's do a kind of analogy here, just regular addition, 48 plus 65. All right, so this is regular addition. Let me just do that in a different color just to emphasize. So we have regular addition here. Okay. So how do we do this in regular addition? 8 plus 5 is 13, right? But we don't put 13 there because 13 is bigger than 10, right? And anytime we have 10s, we kind of give them to the other column. So what we do is we actually keep this 3 here, and then we give the 1 to the other side, right? That 1 representing actually 10, okay? And then when we add the next column, we add that 1. So 6 plus 4 is 10, plus 1 is 11. So we get 113. All right. So we carry that 1. All right. So what we're going to do here is exactly the same idea. 45 plus 18 is what? 63. Right? So that would be 63 minutes. But 63 minutes, we don't want to say 63 minutes, right? 63 minutes is 1 degree plus 3 minutes. Right? Just like, oftentimes in real life, we don't want to say 63 minutes. We say an hour and 3 minutes. Okay? So here we want to say this is 60 minutes. Sorry, seconds. I've been saying minutes, seconds. 45 seconds, 18 seconds gives me 63 seconds, right? And instead of saying 63 seconds, we like to say 1 minute and 3 seconds. Okay? And so we can rewrite this as 60 plus 3 seconds, but 60 seconds is 1 minute plus 3 seconds. All right, so ultimately this 45 plus 18 seconds is 1 minute and 3 seconds, right? So the 3 seconds we keep, just like we kept the 3 when we added 8 plus 5, right? So that guy we're going to keep here as 3 seconds. But then this 1 minute, we carry it over to the other column where we add minutes, okay? And then now we just go to the next column, and we just continue this procedure until we get to the end. All right. So what happens if we add 28 plus 52 plus 1? We get 81 minutes. All right. But again, we don't like to say 81 minutes, right? In real life, in terms of time, we would say maybe an hour and 21 minutes. So we do the same thing here, right? Convert this into 60 minutes plus 21 minutes. Okay, 60 minutes is 1 degree. So this is 1 degree plus 21 minutes, right? And the 1 degree, we just move to the next column as a carry, right? As a carrying term. And let me put a box around this 21 because that's the guy we keep, right? So this is going to be a 21 minutes in this middle column. Let me put a box here just to emphasize those are the guys we're keeping. Okay, and we carry the 1 to the other column. All right, so and then ultimately here we just add 5 plus 2, that's 8, 28 degrees. Okay, so we get 3 seconds here, 21 minutes here, and 28 degrees. Okay, so the sum of these two angles is going to be 28 degrees, 21 minutes, and 3 seconds. Okay, so this is a very nice revisiting of kind of elementary school addition, but in kind of a more advanced form, right? Where we're counting by 60s instead of in elementary school, you're counting by 10s, right? So you're here because it's 13, 10 plus 3, you carry over the 10, right? Here, with the degrees, minutes and seconds, we're carrying over 60s because we're counting in 60s. Okay, so again, in the paper homework, you explore this a little further, where you're counting in 16s and you're counting in 2s. Okay, subtraction. So let's say we want to subtract, right? So we've got, let's say, 42 degrees, 21 minutes, 32 seconds, minus 2 degrees, 10 minutes, 12 seconds, right? And the way we do it, same idea, 21, 32, elementary school, except, of course, in this more advanced situation of, in a way, counting by 60s, all right? The technical term would be we're actually working with base 60 arithmetic for the minutes and seconds. Of course, the degrees is still kind of our regular concept of working with base 10. Okay, so the idea is just as in elementary school, 32 minus 12, that's going to be 20. 21 minus 10, that's going to be 11. And then 42 minus 2 is going to be 40. All right, so no problem for this problem, right? However, of course, we know from subtraction that things can be a little more complicated. So let's look at that example, or an example of that. So this one was easy, right? Oh, by the way, why might we want to subtract? Well, again, in terms of motion, or maybe not in terms of motion. Here's a practical situation. You have one angle here, right? You know that angle right there. You have another angle there, right? And again, you know it in terms of kind of the expression in terms of degrees and stuff, right? Now, what the question is, what is the angle between these two rays, right? Well, it's the big angle minus the small angle. So it's very practical to want to subtract, okay? All right, so what happens here? We have 32 minus 45, and we're not able to do that, right? So again, we go back to elementary school math. If we have 48 minus, let's say 70, let's not do a negative. So let's say 29, all right? How do we do this? Well, 8 minus 9, in elementary school, we're not able to do that. So we borrow a 1 from the 4, right? That 4 becomes a 3, and this 8 becomes an 18, and then we're able to subtract. So this is a 9, okay? And then 3 minus 2 is 1, all right? So what's actually happening here? When we actually go through this procedure, let me rewrite it, 48 minus 29, right? What we're saying is that this 4 actually represents 40, right? So what we're doing is we're saying, okay, I'm going to make it represent 30, but that 10 has to go somewhere, right? So that 10 goes to this 8. So 18, right? 10 plus 8 is 18. And then now we can kind of do, a first grader would now be able to do the subtraction, right? 18 minus 9, all right? So we do exactly the same idea here. 32 minus 45 is negative. We don't really like that. So what we do is we borrow one minute from the column to the left, right? So 20 minutes here, from 21 minutes to 20 minutes here, and we take that 1 minute that we've borrowed and we give it to the first column. So this is going to be 1 minute, which is 60 seconds. All right. Well, 60 seconds plus 32 seconds now can when you subtract 45 is going to be a positive number, right? So now we can do kind of comfortable subtraction without having to think about negative numbers, all right? So one way you can think of this is just like how we made the 8 into an 18, right? 8 is 10 plus 8, 18 is 10 plus 8. We can add the 60 and 32 to get a 92, right? And 92 minus 45 is for sure going to be something bigger minus something smaller. Okay, so that works, but in a way, what you could also do is just say 60 minus 45 is 15, because that one's always going to be a positive number, and then add that to 32. All right, but no matter how you do it, right, you just have to remember it's plus 60 plus 32 minus 45. All right, whatever you get will be a positive number. Okay, so in this particular situation, we're going to get 47 seconds. All right. Okay, so that was the seconds column. Now for the minutes column, same idea, right? 20 minutes minus 30 minutes. We don't necessarily like to work with negative numbers, let's say we don't like to work with negative numbers. Then in that case, we're going to borrow 1 degree, right? So we borrow 1 degree from here, and we give it to the middle column, but 1 degree is equal to 60 seconds. So that 1 degree that we borrowed is now 60 seconds here. All right. So altogether, we can see that if we have 60 plus 20 minus 30, we're going to get a positive number. All right. So again, we avoid having to deal with negatives. So this is going to be 50 minutes, right? And then finally, 45 minus 12 is going to be 3, okay? And so we get 33 degrees, 50 seconds, and 50 minutes and 47 seconds. Okay, so this is a nice way to kind of work this through because we're all used to kind of working with elementary school math. But it might be useful to think of this in a different point of view. So what is 46 degrees, 21 minutes, and 32 seconds minus 12 degrees, 30 minutes, 45 seconds? That's equal to 46 degrees plus 21 minutes plus 32 seconds minus 12 degrees plus 30 minutes plus 45 seconds, right? And so this is 46 plus 21. So we have that, right? And then what we're doing when we're kind of subtracting these columns is we're kind of matching the second terms with the second terms. We're matching the minutes terms with the minutes terms, right? And we're matching the degree term with the degree term. But when we do subtract this and this, right, we do get a negative number. So what we're in effect doing is we're rewriting this 21 as 20 plus 60 over 60 minutes, and that's equal to 20 minutes plus 60 seconds. All right, and then now what we're doing is we're combining the 60 seconds with the 32 seconds so that it interacts with the 45 a little better. Okay, so this is the same thing, but we're kind of seeing it perhaps in a slightly different mathematical form. Okay. All right, and again, of course, this 60 plus this 32 minus the 45 is a positive number. All right. Okay. Of course, you could kind of, in a way, cheat these problems by just converting everything to decimals, subtracting in terms of decimals, and then converting back to minutes and seconds. But it's probably a good idea to learn how to work this natively so that, if you do happen to work with different number systems in the future, you're kind of more comfortable with them. All right. And again, it's very possible that you might in the future, especially if you're going to work with computers in some way. Okay, finally, let's do some multiplication. Oh, sorry. Let me give you one thing to think about here. So what about 47 degrees minus 21 degrees, 42 minutes, and 13 seconds? Right? So you figure this out. Okay. So it's going to be the same procedure, but of course it looks a little different because it's just 47 degrees flat, right? There's no minutes and seconds. So it might not be completely obvious how to work this. And if it's not, think about the analogy with, let's say, something like 10 minus, or let's say 20 minus 13, right? Where the 20 doesn't have a single digit term. Okay, so you want to kind of think about it like that. All right, multiplication. So 12 degrees, 41 minutes, 33 seconds. What's 5 of those? Right? And where might we see this in real life? Well, again, if you're thinking about motion, perhaps you have gears or something like that that move this amount of degrees, right? Every interval. Okay. Now you have 5 intervals, let's say, of time or something like that. Then how far will this gear have turned? Okay. So very, very natural type of question that you might encounter. Okay, so how do we do this? Well, let's just do the same model, right? Use our elementary school math, except again, modified to this kind of more advanced 60-based arithmetic. Okay, so multiplication, right? Oh, by the way, multiplication, starting, if you haven't started already, never use x for multiplication. Use a dot, if anything, or just use parentheses, right? So 5 times 4, maybe you could write it like that. 5 times 4, you could write it like that. From here on out, pretty much, you should never be doing stuff like this, okay? Because it can get very confusing, especially since we're going to be doing a lot of algebra, and we're going to have variables like x, and it's really easy to get confused, okay? So never use x for multiplication from here on out. It's a good habit to kind of get into. All right, so in any case, let's do our multiplication. So how do we multiply regular numbers, right? 42 times 7. We got 7 times 2 is 14, right? That means 10 plus 4, right? What is 10? 10 is, in terms of the first column, 10 is just represented as a 1 because that's the tens column. And so we carry that 1 over there. Okay. And then we do 7 times 4 is 28. And then we add the 1. So we get 29. All right. So 29, 294. Okay. So we're going to do the same thing here. So 33 times 5 is 165. Right. So this gives me 165 seconds, but way bigger than 60. Right. We want our seconds to be expressed in terms that are less than 60. So we convert this to something less than 60 by, for example, dividing by 60, right? If I divide this by 60, I'm going to get 2. So this is going to be 2 times 60, and then plus the remainder, right? So let me actually just do the division here. 165 divided by 60, right? So we got 2 here, 120, and we're left with 45, okay? So what that tells me is that this is 2 times, what this division here tells me is that 165 is equal to 2 times 60 plus 45. All right. So this is 2 times 60 plus 45, right? So these are still all expressed in seconds. But if I want to convert it to minutes, this is 2 minutes plus 45 seconds. Okay. All right. So we can give this 2 minutes to the other column. All right. So 2 minutes right there. Okay, so this would be equivalent to putting this 2 minutes there is equivalent to putting the 1 there. All right, because this, in terms of regular multiplication, this first column here is the tens column. Every number here represents actually 10 of those things. So this 4 represents 40, that 1 represents 10. And here, this 41, right, is the minutes column. So it's 41 minutes and 2 minutes. Okay. All right. Next, for this first column, we end up with just a 45 seconds, right? And we've brought the 2 over to the next column. All right. Next, just like as with regular multiplication, we multiply 5 with 41, and we get 520 like that. 205 minutes. Let's add that with the 2. So let me write plus 2 minutes. Right? So that's going to give me 207 minutes. Okay. Again, 207 minutes is way too big. So let's do our little computation here. 207 minutes divided by 60. That's going to be 3, 180, 27 is our remainder. So again, the meaning of this computation is that 207 is equal to 3 times 60 plus 27. All right? And so the meaning of that is that 207 minutes is 3 times 60 minutes plus 27 minutes. But 3 times 60 minutes is 3 degrees plus 27 minutes. All right? And so this guy here is 3 degrees plus 27 minutes. All right? So the 27 minutes we keep. The 3 degrees, we bring it, we carry it over to here. All right? So 3 degrees. Okay. And so finally, we end up with 5 times 12. That's going to be 60. And then we still have the 3 degrees, so 63. All right, so this is going to be 63 degrees. Okay, that last part is straightforward because, again, when we work with degrees, that's just regular. There's nothing, again, to the column to the left of that, right? So it's just whatever it is, 63 degrees. We don't have to do any sort of modifications. And so ultimately, we get 63 degrees, 27 minutes, 45 seconds as our final answer. Okay. So again, the way I did this was kind of long, right? I did these divisions, for example, over here, and I reinterpreted the division very, very carefully so that I knew to carry the 3 degrees. I think it's probably a good idea, especially when you're not as comfortable with working in this kind of base 60 arithmetic, to work kind of carefully like this here, right? To write everything out very carefully so that in a way you can also see exactly what you're doing, right? We are converting this minutes, right, into degrees and minutes because 60 minutes is 1 degree, okay? So that you're kind of closer to, always closer to working with the concepts in the front of your mind, right? We're working with minutes, we're converting to degrees. Okay, so the last bit of arithmetic is division, and you figure it out. All right, so maybe you can figure out 63 degrees, 42 minutes, and 20 seconds divided by 2. Right? And again, very practical. You might have this angle right here, 63 degrees, 42 minutes, and 20 seconds. And you need to know how to split that into 2 pieces. All right. Okay, so that should be it for section 1.1. As I said, typically we'll be doing 2 to 3 to 4 sections per week, but because this is the first week, I think it's a good idea to keep it a little lighter so that we can all get kind of adjusted to the class.